Okay then, so on to something else that changes the number of alleles in a population, and that's gene flow. Gene flow consists of the movement of alleles among populations. Now, alleles can get transferred through either the movement of fertile individuals or just the gametes, such as pollen. Many plants have pollen that's moved about by the wind, and so the individuals themselves never actually meet. Gene flow tends to reduce differences between populations over time. So as the alleles move from one population to another, if they're exchanging, they tend to become a bit more similar over time. Now, gene flow is more likely than mutation to alter allele frequencies directly. It's because you can get obviously much more movement than the occasional random change in someone's DNA. And here's a very well-known cover of Time magazine where we're looking at a woman. She doesn't actually exist. She's a composite created by a computer from a mix of several races or cultural groups, you could say. And what they're presenting in this article is that this is the new face of America. Now we're talking 1993, quite some time ago, but the flow of immigrants to this country is very well known. So we are one example of how gene flow is overall decreasing the variety overall that we're developing in sort of similar forms. Anyway, now you might say, okay, so gene flow is good, right? It improves a population. Not always. Gene flow can decrease the fitness of a population. And the example they give in your book is an organism called bentgrass. Now, alleles for copper tolerance are beneficial for populations that live near copper mines, where there's a lot of copper in the soil that's generally toxic in non-tolerant plants. Wind-blown pollen moves these alleles between populations. So the movement of unfavorable alleles into a population results in a decrease of fit between the organisms and the environment. So looking at this diagram, if you look to the far left, you see that when you look at the direction of the wind, which is flowing from left to right, some non-mine soil alleles get blown to the locations where the mine soil, the high copper content soil is, and alleles from those individuals that live in the mine soil, their alleles blow onto other areas that don't have mine soil. So in other words, the movement of these alleles, the alleles may be effective in some places, but in the case of this particular instance with the mine soil plants, those alleles are blowing into areas where there is not the copper material in the soil. Therefore, it will tend to decrease the fitness of those plants living in the non-soil areas, non-mine soil areas. And you can see, looking at that graph, the fewer alleles are present as you move to the right-hand side. So it's only those areas very close to the mine that you see that drop-off, okay, where you see very little effectiveness of those plants living in the areas where there is not the copper contaminating the soil. Just moving through these diagrams. Okay, so it isn't always negative, of course. Sometimes gene flow increases the fitness of a population. And one example, insecticides have been used to target the mosquitoes that carry the West Nile virus and the protists that cause malaria. Alleles have evolved in some populations that give insecticide resistance to these mosquitoes. The flow of insecticide-resistant alleles into a population can cause an increase in fitness. Just as people can move about in airplanes, so also move things like mosquitoes. So mosquitoes that have this insecticide resistance, one of the ways in which their resistance spread throughout the population of mosquitoes in this country was, as we're moving around in airplanes, we were also doing things like transporting these mosquitoes around. So it was increasing their fitness because when people finally did start using the insecticides, those alleles for resistance were already there. There was not going to be a mutation event bringing that resistance to that population. Okay, so a little bit more in 23.4. So natural selection, it's the only mechanism that consistently causes adaptive evolution. Okay, so the pressures of an environment acting upon the alleles present in a population, that's what, in essence, if you can use the word, chooses the forms that have the best fitness in a particular environment. So, and we've mentioned this before, so some of this is going to be sort of reviewy. Natural selection brings about adaptive evolution, change of organisms to better fit an environment by acting on the organism's phenotype. So when you hear phrases like struggle for existence and survival of the fittest, they're kind of misleading because it implies direct competition among individuals. What's really happening is reproductive success, okay, to leave more offspring in the environment. So not so much the individuals fighting for each other, it's really relative fitness. Who's leaving the most offspring in an environment? So reproductive success is generally more subtle and depends on many factors. Relative fitness, this term refers to the contribution an individual makes to the gene pool of the next generation relative to the contributions of other individuals. Okay, so who leaves the most kids in that next generation? Selection favors certain genotypes by acting on the phenotypes of certain organisms. Now, there's 3 forms of selection, which I'm going to go into in the next segment.